And today we have Dr. Peng from UC Berkeley, the Department of Statistics, and his research interest and expertise is in causal inference in experiments and observational studies with applications to biomedical and social sciences. And today, Dr. Ding would like to talk about some question on the multiply robust estimation of causal effects under principle ignorability. So let's welcome our speaker today. Please go ahead, Dr. Dean.
Thank you very much for the introduction. Hello, everyone. It's my pleasure to give a talk here on my recent research with my collaborators, Zhichao Jiang and Shu Yang. The title is about multiply robust estimation. I will tell you what do I mean by principle ignorability, because it's a technical terminology. The topic for today is causal inference with intermediate variable. In most cases, causal inference concerns the effect of the treatment Z on an outcome Y, or the average treatment effect. Many applied problems have intermediate variables between the treatment and the outcome Y. So maybe this S is on the pathway from Z to Y. Maybe it just happens between Z and Y. Here are some examples. So S can be the observed compliance status with respect to the treatment in clinical trial. Z is the treatment assignment assigned to treatment or control, and sometimes the patients may not take the treatment. So S is the indicator for compliance status, whether the patient take the drug or not. And in other applications, S can be survival status before measuring the outcome, quality of life. So Z is the treatment, Y is the quality of life. But some patients died before measuring their quality of life. So S is the indicator for survival. And the third example S is called the surrogate endpoint. So we are interested in the effect of Z on Y, but maybe Y is difficult to measure. So we need to wait for a long time to measure Y. So we measure some S. So we hope the effect of Z on S can predict the effect of Z on Y. So that's why S is called the surrogate endpoint. There are two standard approaches to deal with intermediate variables. First one is mediation analysis, which involves so-called nested potential outcomes by Robin, Screenland, and Pearl. The second one is called principal stratification. I will tell you the definition, but there are some review papers comparing these two frameworks. Today I will focus on the second. Okay. So now I'm going to define what is principal stratification. Here are some basics of potential outcomes and intermediate variables. We define two potential outcomes, Y1 and Y0, with respect to the treatment Z, binary treatment Z. 0 usually for control and 1 for treatment. So for every unit, we imagine there are two outcomes. We can observe only one, but imagine there are two hypothetical versions, one under control and one under treatment. And in the end, what we observe is Y. If Z is 1, we observe Y1. If Z is 0, we observe Y0. Okay. So this hypothetical notation is useful for us to think about the problem. So if you look at the definition of the average causal effect, its definition involves potential outcomes. The average of the individual treatment effect. And because of the randomization, Z is randomized, we can put Z in the conditional exploitation. So if you check the simple algebra, some magic happens. The right-hand side only depends on the observables. So it's basically two-sample t-test or two-sample problem. We're comparing the mean of Y under treatment and the mean of Y under control. Nothing fancy because of randomization. But if we have intermediate variables, things becomes tricky. For example, if we have data, like we have a column of Z, column of Y, a column of S, maybe some columns of X, how do we analyze the data? We may say, let's regress y on z, s, and other x, for example. So it seems an easy approach to analyze the data. But many practical, many people working on clinical trials know this is a bad idea. We shouldn't condition on intermediate variable s if the interest is the effect of z on y. Why? Here is the simple explanation why conditioning on s, the observed s, could be a bad idea. If we look at the first line, it's comparing two conditional expressions. So we change z from 0 to 1, holding other things constant, especially holding s constant. Okay, so the second line is by definition, if z is 1, y equals y1, s equals s1, and if z is 0, y equals y0, s equals s0. So nothing changed, just definition. And if we think about randomized experiment, z is independent of the potential outcomes, all the potential outcomes, because when we make a decision whether a patient receive treatment or control, we don't think about their potential outcomes, just random decision. Then some weird things happen, like because z is randomized, we can drop it from the condition. So it's reduced to the last line. We compare the average of y1 and the average of y0, but for different subgroups. So patients with S1 equals S are different from patients with S0 equals S. This is not a causal comparison. You are comparing two subgroups, two different subgroups. This is a very simple explanation based on potential outcomes. This is from Frankakis in the Ruby. So this explains the usual wisdom. Don't condition on S. That's dangerous. One option is to just drop S. Don't use it. But in many problems, we cannot do it. For example, in problems on truncation by this, we cannot drop S because S is a survival indicator. And in surrogate endpoint, we cannot drop S. We want to use S too. We want to use the effect of z on S to predict the effect of z on Y. So we have to use S in some way. And we know we cannot condition on S naively. So what else can we do? This is a proposal by Frankakis and Ruby. They call it principal stratification. Maybe conditional S is called the naive stratification, I guess. So their proposal is to condition on the joint potential values of S. So we condition on U. U is the vector of S1 and S0. Because U, the potential vector is unaffected by the treatment. It seems an outcome variable, but it is a covariate because it happens before the treatment. If we condition on U, we have a standard subgroup effects. For simplicity, let's focus on a binary S. Then we have 4 principal strata. So you can take values, these values, 2x2 combinations. And we define principal causal effects, PCEs, as the subgroup effects. We compare Y1 and Y0, but only for the subgroup with S1 equals little s and S0 equals little S0. We call it tau S1, S0. Depending on the meaning of S, the meaning of PCEs vary. For example, in a non-compliance case, people usually talk about tau 1, 0. 1, 0 means if the patient was assigned to the treatment, he would take the treatment. If he was assigned to control, he would take control. So those patients are the compliers. And in truncation bias problems, because if S is 0, if the patient died before measuring the outcome, then the outcome is not well defined. The quality of life is not well defined. The only well defined subgroup is tau 1. So if the patient always survives under both arms, then we can talk about the effect on Y. This is called the survivor average causal effect. In mediation, not everybody agree with this point. Some people say that for mediation analysis, we should just use the Robbins and the Greenland framework. Some other people think at least two subgroups measures direct effects. For example, tau 1, 1. For the 1 group, the treatment does not change S, but the treatment can potentially change Y. The same thing for the 0 group. The treatment does not change S, but potentially the treatment can change Y. So for these two subgroups, the effects can measure the direct effect of Z on Y, not through S. But the other two subgroups are more complex. The last one for the surrogate endpoint. So if we translate the English meaning of surrogate, we hope the effect of S can predict the effect of on Y. Then we hope tau 1 and tau 0 are small. If the effect on S is 0 for these subgroups, we hope the effect on Y should be small, or ideally should be 0. And the other two groups are not 0 or are large. So in these problems, the goal is to estimate this tau S1, S0. That's our goal for this talk. The definition of potential outcomes and principal stratification seems okay. They seem to clarify something, because not everybody likes potential outcomes. So here is an example. It might be helpful, but it's not clear whether it's useful for data analysis. Like at this moment, it's just definitional. We define things, but the question is, can we estimate those PCEs? It's really challenging because principal stratification U is partially observable. We can only observe either S1 or S0. We never observe the joint values. And now the quantity of interest is conditioning on the joint values, the latent variable. So structurally, we have missing data. This is not because we are not careful enough in data collecting process. This is just because it's missing by definition. And if you look at the observed data, we have mixture distributions. We have 4 observed groups defined by S, Z, and S. So 4 combinations of observed Z and S. Let's focus on the first. In this group, Z equals 1, S equals 1. So we know S1 is 1. That's by logic. But we don't know the value of S0. We don't know the potential outcome or the counterfactual outcome under control for those treated units. So S0 can be either 1 or 0. Okay, so for this subgroup, there are 2 mixture components, 1, 1, and 1, 0. The same thing you can work out the mixture components for other 3 subgroups. So in summary, if I give you the data containing Z, S, and Y, you cannot observe U completely. From the data, you can only tell for each unit. It's either, for example, this one is either 1, 1 or 1, 0. Fundamentally, we have a mixture distribution. And we know disentangling mixture distributions is hard, because in usual mixture problems, the goal usually is not about the component specific quantities. Maybe we are interested in using mixtures to estimate the density, or using mixtures to classification or clustering. We're not really interested in making inference about the mean or variance of each component. But here, that's our interest. We are interested in the value, the average of Y1 or Y0 given the subgroup. Okay, we're really interested in the mixture components. There are some existing strategies. Let me quickly review them. First one is famous in econometrics, called instrumental variable. They assume the following. The first one is monotonicity, assuming S1 is larger than S0. So there's no 0-1 group, because the first one cannot be smaller than the second one. The second assumption is exclusion restriction. We assume tau 1, 1, tau 0, 0 to be 0. So they assume these two effects are away. Essentially, there's no direct effect of z on y, because if z does not change s, z does not change y. The only effect of z on y is through s. So there's no arrow from z to y. It's called exclusion restriction in econometrics. And they show through very simple mathematics, we can identify the complier average causal effect. So the tau 1, 0 group, the right tau 1, 0 as the ratio of the ratio is the average effect of z on y and the average effect of z on s. If we have randomization of z, then we can easily estimate the effect of z on s and the effect of z on y, because that's a two sample problem, and you further take the ratio. That's a simple result. But this simple result cannot be used in general, because tau 1, 1 and tau 0, 0 are parameters of interest. We cannot assume these two effects away in general. In the instrument variable case, maybe that's not too bad if you believe the assumption is plausible biologically, because whether the outcome is improved relies on whether you really take the drug. Does not matter. It doesn't matter whether you are assigned to the treatment or not. So biologically, maybe that's okay, but it can be violated in those non-double-blinded trials. And in that problem, maybe tau 1, 0 is the quantity of interest. But in general, that's not true. And the second strategy is Gaussian mixture or any other parametric mixtures. You can assume mixture distributions. And there are a lot of things you can do with mixture distributions. This is from the thesis of John with Rubin. But this is not a very good idea in practice, because the approach is very sensitive to parametric assumptions. If the parametric assumption is slightly violated, the results can be totally different. And even if the model is correct, inferring components of Gaussian mixture is difficult, and people do simulation to show this approach has poor finite sample property. Okay, the second slide on existing strategy. So the first one is popular in econometrics. If we cannot identify the distribution without parametric assumptions, then we just say we can partially identify the parameter. In the end, we cannot provide a point estimate. We provide a set. Then it's the worst case set for the parameter. The second one is Bayesian approach. Bayesians are usually more aggressive. They are willing to specify, impose a fully specified model and some priors. And you can always simulate the posterior distribution. So there's no philosophical difficulty for Bayesians to deal with this problem, but we know that that must be sensitive to the prior. And also you need a fully specified model. And this third class is use some more information. You have to borrow information from somewhere else. For example, finding some auxiliary variables that are somehow related to your problem, and they satisfy some assumptions. There are a lot of people using this strategy, but it's really case by case. There's no general strategy. And usually these approaches are non-standard in estimation. None of these are widely used due to the complexity in implementation. So I'm going to talk about one strategy. I do not necessarily believe this is the best assumption, because in causal inference, we cannot avoid assumptions. And sometimes we cannot judge whether the assumptions are stronger or weaker, and most assumptions are untestable. The reason why we focus on this class of strategy is because the implementation is simpler. Maybe people can use this as a starting point. And we would recommend sensitivity analysis strategies in the end. This is from applied statistics. People use this analyze data, but we feel the theoretical foundation is not solid enough. So there were two papers focusing on simple cases like completed randomized experiment. And I will focus on a more general setting we allow observational study. If we allow observational study, we have to impose stronger assumptions. For example, we must first assume conditioning on X, treatment is independent of all the potential outcomes. That's called ignorability. If we do not even have this assumption, we give up with estimating the average effect of the on Y. That's a usual assumption. This is a strong assumption. If we read it in this way, this means given X is randomized. That's a really strong assumption. You do not have randomization, but you assume your observational study is hypothetically randomized. That's usually disappointed people. Okay, the second assumption following the instrument variable literature will assume monotonicity S1 larger than S0. We can relax it, but things will become complicated. The third one is the key. It's in the title called the principal ignorability. That's why every time I give a talk on principal stratification with very high probability, I will lose the audience because there are so many terminologies. And it basically says these two conditional expressions are the same, and these two conditional expressions are the same. So what do they mean? Let me give you more explanation. Okay. I already reviewed the first assumption. It's standard. We have to assume it. Otherwise, we give up. The second one is useful because monotonicity simplifies the mixture distribution. It rules out the 1, 0 or 0, 1 group. In the non-compliance case, this is called the defiers. If it's 1, 0, it's called complier because those patients comply with the treatment assignment. And these patients are the defiers. They just take the opposite. That's the weird group of people. They just do the opposite. They just didn't listen to the doctor. And this assumption simplifies the mixture distribution. If you look at the 2x2 table, if Z is 1, S is 0, you know this must be 0, 0, because this one does not exist. If Z is 1, S is 1, you know this must be 1, 1. And this is helpful because even though we don't know the U value for everybody, at least we know the U for somebody here. Then we can identify the probability of U equals 1, 1, and maybe given X. We can also identify the probability of 0, 0 given X. And because the only remaining term is 1, 0, we can also identify the probability of 1, 0. So it helps to identify the probability, although it does not help to identify the individual U. Okay, so the final one is assuming these two components and these two components are the same. It means a conditioning on X. Okay, so if it's really very strong, you have a mixture problem, you assume it away. And there's a stronger version saying U is independent of Y. This was imposed by those applied papers. And we only need the conditional expressions. And we call it ignorability because this is in some sense in parallel with the standard ignorability assumption. Like Z is randomized given X, and further, U, the indicator of U is randomized given X. It holds only when we have enough background covariance. If you think the difference across those components are fully captured by X, then you might be okay with this assumption. But otherwise, you won't be happy with this assumption. But we will start with this assumption, but conduct sensitivity analysis later. As I mentioned before, this is because the inference is relatively easy. We only need to fit standard statistical models like linear model or logistic regression, and you put them together. You have estimator under this assumption. It may be a good starting point. Okay, let me introduce some notation, more notation. This time is mathematical notation. So we have variables X, covariance, Z, treatment, S, intermediate variable, Y, outcome. So everything should be conditioning on X. Then we have three pieces of the likelihood. Conditional probability of Z given X, this is pi, called treatment probability, usually called the propensity score. But we don't use propensity score because we have another score called principal score, which is the probability of U given X, the probability of the latent strata. And as I briefly mentioned in the last slide, we can identify those E's by the P's. P is the probability of S given Z and X. Because there is a one-to-one mapping between E and P, so later I won't distinguish them, just call either set principal score. The final piece in the likelihood is we only need the mean, so it's a conditional expression of Y given Z S X, we call it mu. So pi E P mu. The first one, how do we identify the parameters? Three parameters defined as the difference of Y1 and Y0 given mu. So in total, I have 6 conditional means. If we understand one of them, we understand all of them. So let's focus on one of them. Y1 given U equals 1, 0. Okay, so this is from the observed data. Z equals 1, S equals 1. It contains 2 components, 1, 0 and 1, 1. Okay, but now we only care about 1, 0. The formula is weighted average of the outcome Y for Z equals 1 and S equals 1. This term is standard. This is the standard inverse probability weighting. So pi is the probability of Z given X. Because treated group and control groups are different, we have to adjust for the inclusion probability, standard IPW. And the additional weighting we have is due to the mixture. This is weighting not by the inverse probability, it's by the probability itself with some standardization. And this weighting is bounded. And we know the inverse weighting can be dangerous in practice, but the new weighting is okay. It's not inverse. And based on this formula, the weighting formula, you can construct the Horvitz-Thompson or the Hayek weighting estimators. And you can do the same thing for all other quantities. The formula is not important, but the important thing is this formula only depends on 2 things, the treatment probability pi and the principal score. It does not rely on mu. Okay. There are 3 pieces in your data, Z, S, Y, but the formula only relies on and is the model for 2 pieces. There are 3 pieces. In total, we have 3 choose 2. You may imagine we have 3 strategies. The second strategy, again, the formula is not that important. The important thing is this formula only depends on treatment probability and outcome mean. So it depends on pi and mu. There's no E and P. No E and PX. Okay, there are P, but not PX. There's a model for S. And how do we understand the first one? And this coefficient here, if you calculate the conditional expression, this is the conditional probability of 1, 0 group given X. This is the standard inverse probability weighting formula if you are interested in estimating the effect of Z on S. This is basically the average effect of Z on S. This is the average effect of Z on S given X because Z only change this subgroup by 1 unit. Z does not change the S value of other 2 subgroups. Okay, and this quantity by principal ignorability equals. This is definition. This equals the subgroup conditional average. This is a conditional probability. This is conditional average. If you take weighted average, you get tau 1, 0. Okay, and also easy to construct estimator because you just replace expression by some by average. Okay, here you only need to model Y and S. the last one. The last one of 3 choose 2 is this formula depends on principal score and outcome mean. There's no pi in this formula. And similarly, this is the subgroup mean, and this is if you condition on x, this is the probability for 1, 0 group. And it's also easy to construct estimators. Okay. So these are just mathematical exercise telling you can play the game. There's 3 pieces. You only use 2, you can get some formulas. But we know if you have two estimators for the same parameter, you have infinite many estimators. Now you have 3 estimators, you have infinite many estimators. Like you have any convex combinations. We'll give you unbiased or consistent estimators. And there are even more estimators. How do we combine them? Or what is the principal estimator? That's a problem of having too many choices. In practice, we don't want too many choices. We just want one. There are some strategies in econometrics, like called generalized method of moments. There are so many moment constraints, we just combine them. And actually, it's a good idea in some problems. For example, this paper is about the standard observational study. How do you estimate the effect of treatment on some outcome in observational study? And this paper shows if you use generalized method of moment, combining infinite many moments, you get the Robbins doubly robust estimator. Okay, so let me review a little bit about the doubly robust estimator, because the title claims triply robust or multiply robust estimator. The initial idea is from Robbins. But Robbins derived double robust estimator not because they are interested in double robust estimation initially, because they are interested in efficient estimators. Okay, so their principle was efficiency. In standard observational study, it's well known we can estimate the effect of Z on 1 based on 2 strategies. First, based on regression. This was done every day by social scientists. Just regress Y on Z and a bunch of covariates, and they claim the coefficient is causal effect. Okay. The second one is inverse probability weight. If you do not believe your outcome model, you can fit a propensity score model and do weighting. But you have to believe your propensity score model. So a clever combination of these 2 is called the doubly robust. And Robbins derived it from calculating the efficient influence function of the parameter of interest. Okay, well, let's try doing the same thing, derive the efficient influence function for the PCEs. Hope they will guide us to construct more principled estimators. Hope they will be triply robust, but we don't know a priori. Okay, let me introduce some notation. This is an awful notation, but it will simplify our discussion. Otherwise, the discussion later will be even worse. Okay, this is the phi notation we use, indexed by this f. So you can imagine we are estimating expectation of this quantity. This quantity can be a function of the covariance and the potential outcome, y and s. Under ignorability, we can prove the efficient influence function for estimating this quantity can be written as this. This is the uncentered one. Okay, so the first part is the inverse probability weighting part. Treatment indicator weighted by the inverse weighted by the probability. This is FYSX, because in your data you don't have potential outcomes. You can only have observed data. So you have to replace it by the observed version and center it by the conditional expectation. And you center it and then turn back. Okay. This would be the efficient influence function for this parameter. And this will help us in the formulas. There are some examples, special cases. If you write phi S1 as the inverse weighting, and S minus its conditional mean, and add the conditional mean back. I will give you some intuition later. Why are we doing this? This is called the classical doubly robust formula, because you replace, if you use the sample mean of this quantity to estimate the mean of S1, you can show it's doubly robust because you only need either the propensity score model to be correct or the outcome model to be correct. You don't need both. And another example, just for fun, you can write phi y0 S0 more explicitly. Okay, so remember the phi notation. It's quite involving, but the formula later will be even worse. We can do the calculation of efficient influence function, obtaining. This is not phi. This should be psi. Okay, this is phi. I'm not good at Greek, so just the notation. This is the EIF for tau 1 0. Phi can be written as something like this. And we know efficient influence function must have mean 0. And there are something I need to explain. This is the phi we introduced for S1, S0. This is the new quantity defined below, depending on those C's and the principal score and those conditional means. I don't have any intuition for this formula, but at this moment, I will give you some intuition later. Because EIF has mean 0, we can rewrite tau 1 0 as the ratio of the expectation of this difference and the ratio of the expectation of this difference. Okay, so I hope you still remember the order estimator I reviewed for instrumental variable. So the order estimator, there was difference in means of y divided by difference in means of s, that's tau 1 0. Now it's similar. The denominator is still like difference in the mean of s, but it's the fancy version. It's the double robust version, or the efficient influence function version. And the numerator, it's quite complicated. It's something like this, depending on everything. And we can easily obtain the ratio estimator by replacing the expectations by the sample means. And the estimator depends on everything. In the joint distribution depends on pi, obviously, because the phi depends on pi. Depends on pi, principal score depends on outcome model. It depends on everything in the likelihood, joint likelihood. Seems more complicated than the estimators I reviewed in the beginning. But this formula is a little crazy in some sense, just from some boring calculation. There's another motivation, maybe helpful. This motivation also motivated by a simple case. People, how do we understand the double robust estimator? People understand it from survey sampling idea called the model assisted estimation. This is also well known, maybe for several hundred years. How do we use supplementary information to improve efficiency in survey sampling? Let's focus on tau 1 0 and rewrite it in terms of access ratio. Okay, by definition, we can do this. There are 4 terms. We focus on the denominator and the numerator, and by symmetry, we focus on this term and this term. Okay, first, how do we estimate this term? We don't use the sample means. We use the double robust formula. And where does it come from? The first line is the simple decomposition minus something plus something, not changing anything at all. The second one, you don't have S1 in your data because this is a potential outcome. You only have X under treated group. Okay, then if you use the treated data, you have to do inverse probability weighting. Okay, replace the first term by weighting, leaving the second term unchanged. Okay, if you look at this is just the double robust formula I reviewed here. Okay, you don't need to do that tedious calculation, and you can recover Robin's formula. And this formula really follows from one line of weighting formula. And this type of decomposition is well known in survey sampling. Like you fit some model to get a residue, and you have a larger data set to estimate the second component, maybe from the census data. You can improve efficiency. And even if the model is wrong, your estimation will be more efficient. It's still consistent and more efficient. That's why it's called model assisted estimation. So the denominator can be written as what we want here. So let's look at this term. How can we recover this ugly formula here? We'll do the same thing. If you understand the simple decomposition before, this is also simple. You minus something and plus something. Obviously, you must minus the conditional mean. And be careful. This 1, 0 is for the latent u. This 1, 1 is for the observed z equals 1, s equals 1. Okay, because this subgroup contains 1, 0. And we use the inverse probability weighting for the first component because this involves y0. You only have treated data for 1, 0. You must do weighting. So we use the weighting formula from identification strategy 1 at the beginning. There is a formula only involves pi and principal score. Just apply that formula. Now for the second component, we rewrite it in this way. This is a funny formula because this is the indicator. This is difference in s. They are the same because this indicator is 1 if and only if u is 1, 0. And this is 0, this is 1 if and only if u equals 1, 0. Because for the other latent u, s1 minus s2 is 0. Okay, so they're equivalent. Now you can replace this s1, s0 by the efficient influence function we discussed. Okay, if you do this, put them together, this plus this, you can recover the formula. Okay, so this formula is not too bad, intuitively. These are based on different theoretical ideas. The first one is efficiency, and this is a weird notion of efficiency, to be honest. It's called a semi-parametric efficiency. It's efficiency in your minimax sense. It may not be the efficiency in your mind. When you do simulation, usually double robust estimators are not efficient, especially when the outcomes are correct. Okay, it's actually different. The second idea is from survey sampling, from model-assisted estimation, initially trying to improve simple inverse probability weighting. The more interesting property of this estimate is robustness with respect to model misspecification. That's a major contribution by Robbins for the average causal effect. A similar result for us is the estimators based on EIFs are triply robust. In the sense, it's consistent. If two of the treatment probability, propensity, principal score, and outcome means are correctly specified, you don't need all of them. Although the estimator here involves everything, but its consistency does not rely all of them to be correct. Okay, this is called triply robust. And Jitkin and Shipser did something similar for mediation analysis, not for principal stratification. Here are some obvious extensions. We extend to randomized experiment. This is independent of everything, including covariates. In this case, it's simpler because we know that treatment probability is known by design, it's constant. But the EIFs are not changed. And we can do the same thing, use the same formula, but the properties are strengthened from triply robust to doubly robust because this model must be correct. We only require either principal score or outcome mean to be correct. And there's another special case called the strong monotonicity. It holds automatically sometimes. For example, in the one-sided non-compliance case, patients in the control arm have no access to the treatment. The S0 must be 0 by design. Okay, we can easily modify the formulas I omitted the details in the paper. The more interesting thing is sensitivity analysis, because I mentioned at the beginning, nobody should believe the assumption. Nobody should believe any of the assumptions in causal inference because they're untestable. And we measure the violation from the principal ignorability by the ratio. There are many ways. For example, you can measure by the difference. By the ratio is the tradition because it is closely related to log linear amount. There are two sensitivity parameters measuring the ratio of this conditional means. Maybe for simplicity, you can just assume epsilon1 and epsilon0 to be constant. Then you can easily display your plots of the estimates as a function of epsilon1 and epsilon0. And given the sensitivity parameters, we can repeat the process to derive the EIFs to motivate the estimators. Okay, again, it's tedious, but the idea is the same. We do the same tedious calculation to derive the EIF. The denominator is unchanged, but the numerator is modified by something. And I don't want to give you the full formula because that's too bad, too tedious. It depends on those sensitivity parameters in some way. Okay, and we can prove this derived estimator is doubly robust, given the sensitivity parameter and the principal score is consistent if either the treatment probability and outcome mean is correct. Okay, so before I said triply robustness is strengthened to be doubly robust. Here is actually weakened. So the name triply robust or doubly robust is misleading. Sometimes triply robust is better. Sometimes triply robust is worse. Okay, so we just follow the literature. People use this terminology, although we don't really think it's a good terminology because it's confusing. Maybe we should say it's two-way robust. There are two ways to make this estimator consistent. Okay, here is also two ways to make the estimator consistent. Okay, let me give you some examples. Sure. The first one is standard from David Card's example of estimating the causal effect of education on earnings. This is from the US National Longitudinal Survey of Young Men collected in many years ago. Sample size almost 3,000. His idea is quite clever. Use the geographic variation in college proximity as the instrumental variable. Okay, because we know estimating the causal effect of education on anything is hard because education, like people go to college or people get a PhD or something because maybe their ability is higher than people not going to college. There are some things we cannot measure fundamentally. Then how can we estimate the effect of education? And Card proposed this instrumental variable, saying the geographical variation in college proximity have some influence on education. Like living or growing up near a 4-year college may increase the chance of going to college. But maybe they believe there's no direct effect of living or growing up near a 4-year college. There's effect on earnings. So there's no direct effect. The effect is through education. That's his argument. Okay, Z is the indicator of growing up near a 4-year college. S is the indicator of receiving education, and Y is the log of age. And you may disagree with his argument of instrumental variable because people choose where to live. There are some hidden things we cannot even measure about the geographic variation in college proximity. Okay, so there is some counter argument for this validity of instrumental variable. But at that time, people really were convinced by this choice of instrumental variable. And we think this is interesting, and we are slightly skeptical.
Sorry to interrupt. I guess we probably have to wrap up a little bit within, like, say, 3 to 4 minutes.
Yes, I can do it. This is the example section. Yeah, okay, thank you. Yeah, so we are a little skeptical, even if we condition those covariates, we think maybe the instrumental variable assumption is violated. Let's try to use the data to test it. Okay, and test under our assumption, we can test whether the effect of Z on Y is 0 for these two subgroups. Okay, and from our analysis, we cannot reject at least. So for these two subgroups, this is the probability. There are 5 estimators to estimate the effect. So the final line is the estimate we'll propose in the end. In the middle, there are a lot of estimators. So the first two are motivated by the first strategy, like treatment probability and the principal score. There are two weighting formula like Horvitz-Thompson and Hayek. This is based on treatment probability and outcome model. This is based on principal score and outcome model. But in the end, we have 5 estimators. They all agree for this two premise. There is no effect. Probably the instrumental variable assumption is plausible. For the first subgroup, it's a little weird. And the first estimator is totally crazy, but it's not surprising. Based on our simulation, the naive IPW estimator, the Horvitz-Thompson one, is crazy because whenever you have some small probability in the denominator, your final estimator is destroyed. Okay, we never recommend this estimate. And even across other estimators, the significance are different. Sometimes significant, sometimes it's not. So overall, the evidence for this subgroup is quite weak. The evidence for education on earnings is weak. But this may be due to the small sample size. So originally the sample size is 3,000, but if you look at this subgroup, it's only 7%. The lower confidence limit is 3%. There are only 90 units in your data. So it's really difficult to get it significant with such a small sample size. Okay, this is the first example. If I have 2 minutes, I can go through the last example. The second one is about the causal effect of flooding on health. The causal effect of flooding on health through, this is from flooding data from Bangladesh. Z is the indicator of severely affected by the flood, and S is the indicator for per capita calorie consumption of the household, indicator smaller than 2,000. And Y is the number of days of a child having diarrhea. And X is covariates, contains a lot of interesting covariate information. And here is our estimates. Again, for this 1-0 group, the proportion is too low. It's hard to get it significant. The only significant subgroup in this data is the 0-0 group. So how do we interpret this? So the treatment effect of Z on the outcome. So the flooding affects the days of diarrhea only for those households with high calorie consumption. They always have high calorie assumption, regardless of the flooding or not. Okay, so they eat a lot. Maybe they have higher chance to get infected by the bacteria. So they have negative impact on the days of having diarrhea. That's our conjecture of the mechanism. Okay. So we can extend the discussion to more general problems like this. Here is on average causal effect. You can talk about anything you want, any function of the potential outcome, including quantiles. The second one is general S. Here we focus on binary S, but what if we have a continuous S? Then we have infinite many principal strata. It's more involving. It requires us to model the conditional density instead of only the conditional probability. So we can do some technical extensions. Okay. These are the papers. One is published, the other is still on archive. Okay, I will stop here.
Okay, thank you very much for your talk. So now we can take maybe one quick question for Dr. Dean. Anybody has a question to ask, please just go ahead and unmute yourself. Anyone?
Hi, if I may,
Yeah.
can you
Please.
elaborate a little bit on the treatment ignorability assumptions? Because I'm a little bit confused on there.
Yeah, I'm sorry for this. Let me explain, because this somewhat standard for the community of causal inference, but it may not be standard for other people. So treatment ignorability is a standard thing in observational study. How can we make progress with observational study for causal effects? Because you may think restricted units and control units are totally different. They're not comparable. There's no way we can make progress. This is one sufficient assumption we can make progress. And conditioning on X, the treatment is randomly assigned. It's independent of potential outcome. In the same way as a randomized trial. When we do randomized trial, Z is randomized. Z is independent of the potential outcome, not independent of the observed outcomes. Okay, that might be confusing when you first look at it. If Z is independent of the observed outcome, we just assume there's no effect, but it's independent of the potential outcomes.
Oh, that makes much more sense. Thank you.
Yeah, this is somewhat standard, but it's really non-trivial and it's just confusing when you first read it.
Okay, so anyone else want to ask a quick question? We've already run 2 minutes past our time, but if somebody has any quick question, you can just pop up. Or if no, then let's thank our speaker again. And I think that's it for this week's statistics seminar. Thanks, Dr. Dean.
Thank you very much.
Bye.
Bye.